Hello. Well, it looks like we can start. Welcome back, everyone. So for today's class, we're going to be moving into the last section for chapter 3. After that, we turn over to chapter 4, applications of the derivative. That'll be a shorter one. And then chapter 5 is moving into the next concept of integration to round out the course. But the bigger announcement is we have our exam 2. It's going to be next week. That means next Tuesday, there won't be class. If you're in the online section, Zoom won't be running. All we're really doing is getting through the exam. You'll have instructions that were already sent to you through the Canvas messaging system. So see here for those instructions, but if you have any questions, if you can't find them, just email me and I'll be happy to help out. If you're in the in-person section, it'll just be in the classroom as usual. And I think we mentioned this before, but it's important to reiterate. There is a bit of a fairness issue that comes from running 2 classes in person and fully online at the same exact time, when some of the class does it in the testing center and some of the class does it in the classroom. The testing center requires flexibility, so I can't just say everyone must schedule on the 10th, because it might not work with your schedule and the testing center could literally fill up. So exam 2 is open to be scheduled from Monday. If you want to take it early, just get out of the way. The day of the exam, Tuesday, is the official day, and it can be taken as late as the 12th. And that's the fairness issue. For the people in the in-person section, I'm only offering the exam in the classroom on the 10th. But if you would like, I can send, even for the in-person section, an exam to the Idaho Falls Testing Center to be taken either on the 9th through the 12th as well. Just let me know and I can make that happen. That way, there's no kind of different kind of weird issue from one section to the other, being forced to do it on one day versus everyone else having a range of days to schedule. Well, just like before, these are the materials. We'll be doing the same thing for exam 3, the same thing with the final exam, maybe even more, maybe a version 3 for the final exam as well for these documents. But any questions at all, folks, about exam 2 or otherwise? Okay, maybe just a bit of advice for about the exam. Standard things to say is to be prepared for it. Be sure you're caught up on the WebAssign for these sections. It'll give you a good idea of what's going to be on the exam. Get caught up on all the quizzes, even though quiz number 6 isn't on exam 2, it'll be on exam 3. Getting caught up on quizzes up to 5 is going to be a really great idea. And as far as the questions go, the questions that are on a real exam are going to be similar to the ones you did in WebAssign, similar to the ones we did in the lecture notes, as well as these documents here. But I'm not going to ask a really long question. You've noticed that some of the questions got really big, taking up practically a whole page. Some of the questions you've done in WebAssign get really long as well. But on the exam, I'm going to keep them kind of short and sweet, kind of similar to how you've seen, say, product rule, chain rule, quotient rule on the quizzes. They're going to be pretty direct, a chance to show you understand the concept of the product rule and all the various other ones, and not get bogged down in the algebra. So if you got through all the homework assignments through these sections, you've done some of the harder questions, harder than what would be on a real exam too. But I guess that's the end of my spiel for that. Next, we're going to look into differentiating logarithmic functions. And that's where these review materials, these documents here, actually were intended for, section 3.7, but I felt like they were good to have available early. Any information we need about logarithms, I'll put them into the notes as we're working through them. So we're going to review this information as we go. And here's how the notes start out. Let's maybe hide example 1 just for the moment, while we focus on the formulas. We start with a base that's positive, not equal to 1. That allows us to define both a logarithmic function and an exponential function at the same time. In the column on the right, this is just for the sake of putting on paper what the formulas look like, but this is actually exam 2 content right here. The derivative of the exponential, base e, and derivative of any other base. Couple examples. Yeah, it's not actually a formula now that I think about that. That was meant to be a formula. Let me write it out this way. If it's any base whatsoever, the formula should look like this. I don't know why that didn't look weird to me until I'm talking about it with you now. Okay, so that's the actual formula. We'll put an example to the right, like what we had where there was a 2. So the column on the left, those are the new formulas. This is the stuff that you're going to see on exam 3. And here's how it goes so far. Let's focus on the nice one. Just like how there's a nice derivative of an exponential. If it's to the base of e, the derivative is just e to the x. And now on the left, there's also a nice logarithm. If you see natural log x, just for the sake of the review on that, ln x, all that means is log to base of e of x. So the French have a hand on the naming of this. They would say logarithm naturel or something along those lines. I don't speak French well. That's why we say ln instead of natural log. You'd think that'd be an nl. So the French have this pat as a ln. And that's all this is saying. If you take the derivative of the natural log n, that's not the world's worst derivative. It's kind of nice. All that happens to x is it goes right down into a denominator. But if it's any other base than base e, x still goes to the denominator, but we multiply by the natural logarithm of that base. So that part right here is analogous to this portion right here when we were differentiating the exponential function. So those are 2 sets of formulas. We'll do a couple examples and then look into the larger examples below. But any questions at all, folks, with these 2 new formulas here and here? Okay, well, it's kind of hard to do an example of this one down below because that's the whole problem. The derivative of natural log x is just 1 over x, and there's not much more to say to it. But maybe if the function looked like this, y equals 10 natural log x. Now it looks a little bit different, but it's the same idea. If you differentiate that function, I'll call it a y prime or a dy dx if you prefer. Because 10 is multiplying, 10 stays exactly where it is. Then you take the derivative of natural log x, it just throws x into a denominator. So you get 10 times 1 over x. Or in a more simplified form, that's just 10 over x. And we often just skip right down to that step, throw x right into the denominator. So that's the whole story on that one. Much like there's not much to say about this, derivative of e to the x is just itself. It gets messy when we look at these problems right here on the top row. If we had a function up here that went maybe y equals log base 10 of x, oop, that was meant to be enter, then the formula here tells us differentiate this and you get y prime equals 1 over x. But then there's more to the story. You have to multiply that x already in the denominator by the natural logarithm of whatever the base is. So this would be 1 over x times the natural log of 10. So that's the easy step to mess there. And it's analogous to what we've seen in the past. We've differentiated things along these lines. If y equals 7 power of x, then y prime is going to be 7 to the power of x, but then we multiply by the natural log of the base, 7. So those are the formulas on the left that are brand new. Formulas on the right are here just to put them in context with the function versus its inverse on the left, and same in this case here. Well, any questions, folks, with these formulas at the moment? Okay, now it can get a little bit messier if there's more going on, if it's natural log or a log base b, but there's more than just x there. Essentially, what we'd be practicing in that case is working through the chain rule in the function. So that's what example one, well, maybe not quite example one, that's what the next coming examples are going to be all about. The example one's more of a compare and contrast kind of problem. I guess there is a chain rule there if you look really carefully. We have two functions, the cube root of natural log x, that exponent might be kind of hard to see, let me bump that up. And a second function, g of x, is the natural log of the cube root of x. And it almost sounds like we said the same thing, but on paper, these are very, very different functions. In fact, the one on the right is the easier one to work with. Let's do the g of x function derivative first, and then we'll come back to the f of x function. So first thing I'd want to do to g of x is rewrite this. G of x is the natural log. We found that exponents expressed in radical notation, cube root of x, are just not easy to handle in calculus. So we switch the exponent into exponential form. That's really a power of 1/3 when we see the cube root. But the moment we have that on paper, we have a fantastic formula for logarithms. We can say natural log, or really any logarithm whatsoever, let's say it more generically, log base b of a for anything to some exponent, I'll just call it r, can be rewritten as r times log base b of a. And I think we've only used that formula about once in class so far. That exponent r is analogous to that exponent of 1/3. If you differentiate this function right as you see, it's a chain rule problem. But logarithms are kind of special. Sometimes you could take something that is a chain rule problem and completely sidestep the chain rule whatsoever. Take that power of 1/3, it can come out to the front as now a coefficient. So now it's 1/3 times just natural log of x. And the moment we've done that, this derivative became way easier. You're just going to take the derivative of natural log x. There it is. You're going to get x in the denominator, and then multiply it by 1/3. So at this step, we finally did the derivative. It was just algebra above. G prime of x. I'll write 1/3 like that. And the whole punchline to what's happening right here is x goes right into a denominator. So this x just goes right down below like that. And we typically would just end the problem in this way. Derivative of 1/3 natural log x is just 1/3 times x. Well, any questions at all, folks, on the part G problem? I'm not sure why I called it part G, but rather the g of x function differentiation. So this one's nice, and this kind of tells us what the theme is in this section. The theme is look before you leap. Really good life advice, especially when you're taking derivatives involving logarithms, because some of the problems you're going to see in the homework are not meant to be as intense or difficult as you might think. Use properties of logarithms as much as possible. If a property of logarithms applies to a problem, it will absolutely, guaranteed, make that problem way easier to navigate. But then that takes us to f of x. There is no property of logarithm for that one. It's kind of unfortunate. If you do this, it's now a function composition that cannot be untangled and unsimplified. And the reason is the cube root is not acting on x. It's acting on the natural logarithm of x. Here, if something is happening on x, that's a logarithm property. But on this one, the best we can do to simplify f is just to rewrite it as f of x is natural log x to the power 1/3. And there's no way to move that 1/3 unless it's affecting x itself, which it's not. If you give a value, like say 5 for x, the first thing you do is take the natural logarithm, then you raise to the power of 1/3. What that means is this problem is just a chain rule problem. It's unescapable. So let's run through the chain rule analysis on this one. There's an outer function and there's an inner function. I believe we use blue for all of our outer functions. And that's this one, the power 1/3. So that's function 1, outer. The inner function is just the thing inside, the natural log x. Not as tricky to spot like it is for the exponential functions. So that's function 2, inner. So we'll follow this ordered as we see it when we do the chain rule. And here's what it's going to look like. Now, finally, at this line, we're taking the derivative. F prime of x. First, we're going to use the power rule. 1/3 comes down. The new power we're going to get is 1 less. So we subtract 3/3 from that quantity and get negative 2/3. But then we have to multiply by a brand new derivative. And this is the derivative that gets chained on per the chain rule. So even though there's going to be no logarithms whatsoever that you differentiate on exam 2, this is still a good review of how any chain rule really goes. Just imagine it's square root x on the inside instead of natural log x, but it would be the same exact kind of process. So take natural log x, we'll drop it here and here. So we're nearly done. We just need to work through that last derivative. But here it is still up at the top. When we differentiate that, it just becomes a 1/x, and then the whole problem is over. So the derivative of f at x altogether is 1/3, and it's always going to be up to you. It's a judgment call if you want to force that to be a positive exponent, drop it down into a denominator, but I'm completely okay with you just leaving it as a negative exponent. It's not a bad strategy on exam. That way you're not getting bogged down with too many algebraic steps. You're focusing on the calculus. So I'll leave this one as natural log x to power negative 2/3 times 1/x. That's the whole derivative. And again, this would be an acceptable answer. If you saw this question on exam 3, left it like that, I'd be very happy with that answer. But if it just looks kind of weird and jarring to you, here's another way you could write it. If you decide to, in fact, simplify further, you could go 1. That's all it's going to be in the numerator. 3 is going to go below because it was already in the denominator. It'll multiply this x. I'll put it out in front. You could force this exponent positive by writing natural log x to power positive 2/3. But like we've done before, I want to emphasize both answers are full credit and very acceptable. Well, that's 2 interesting derivatives so far. And the takeaway with this, the reason we did 2 problems in one is, notice how severely different the derivatives become if you just make one small design change. If you're cube rooting the entire natural log x versus the natural log of cube root of x, these are completely different functions, really. And it's reflected by seeing how their derivatives are also quite a bit different. This one includes natural log x to power 2/3 in the denominator. Well, our goal is just to practice doing more logarithms as we get through these. Any questions so far, folks, before we try some more? Okay, here's the next list of derivatives we're going to take a look into. It says compute the derivatives of the given functions, use properties of logarithms where possible. And because we're using so many properties of logarithms, let's pull up the sheet on that. I probably should have done that before class. I kind of just forgot to do this. I want this document right here, logarithms review material. We'll take a short mental break as you watch me resize this. The major things I want to focus on are not so much the change of base formula, these are nice rules right here, but this table highlighted in yellow pretty much just captures in one nice little neat spot everything we need to know for using the properties to simplify functions. So let me just resize this a little bit better. Okay, so now back to our function, this one down here. When we look at that function, there's lots going on, and the hint says we definitely want to use properties of logarithms where possible. It's just as important to know when you can use properties of logarithms as it is to know when you can't. And this is the no good case. Addition and subtraction of stuff has a way of just messing up algebra. For example, a plus b squared is not a squared plus b squared. You have to FOIL the whole thing. Same issue with this natural logarithm right here. No property whatsoever on the left here talks about adding an x plus y. So that's kind of a bummer. We can't use properties on this one, but we absolutely can on part B. So we'll come back to the properties when we work through that one. Now this one's going to be a chain rule problem, but just for the sake of comparing and contrasting once again, this derivative is very similar to a derivative we've already seen before. Let's suppose, just for the sake of reviewing and comparing, we had a different function, y equals square root of 9x power 7 minus x power 6 plus 5x minus 11. For the derivative on the left, we have the formula that says derivative with respect to x of natural log x is just 1 over x. And that's a really nice derivative. But for what we have on the right, if we focus on just the square root function, we've cited this formula a couple times in the notes already, which says the derivative with respect to square root of x. It doesn't work with the cube root as we've discussed before. But for square root x, this becomes 1 over 2 times square root x. That's kind of interesting in how similar that looks, right? For the natural log, x just goes into the denominator. For the derivative of a square root goes into the denominator, but with a factor of 2 at the same time. So that's the new problem on the left. The old problem on the right, essentially an exam 2 review question. Let's do this review question on the right, and then we'll see how this one goes on the left. So for the one on the right, it's a chain rules process once again, and the inner function is this one here, 9x7 minus x power 6 plus 5x minus 1. Because it's the inner, we do that derivative second, so we put a 2 on it. There's also an outer derivative. It's kind of hard to highlight. It's the square root function. So this function, the square root, is derivative 1 outer. And you could write it to power 1/2, like you might have done for, say, if this was a 5th root or a 7th root, and you don't have a formula like this one above. But in that format, we can say, let's go with dy dx, just to mix in some Leibniz notation. The derivative of y with respect to x will follow this order, outer derivative first. So it'll turn into, well, what does the outer derivative do? Here it is, the shortcut right above where the red dot is. It's 1 over 2 times the square root of something. Then this part's the chain rule, multiplied by the derivative of whatever that something was. And the something that goes both here and here at the same time is the inner function. So we copy it into both positions. 9x7 minus x power 6 plus 5x minus 1. And then again. Barely had space for that. Let me know if that's kind of hard to read. I think I kind of wrote it small to squeeze it in. So that's step 1, derivative of the outer function. Inner function plugged into both positions, here and here. Now we just finish off this one. And when we do this derivative, because it's multiplying a fraction, it just multiplies into the numerator. So you get that dy dx altogether is now 2 over root 9x7 minus x power 6 plus 5x minus 1. Then this derivative is nice. It's just a polynomial. You get 9 times 7, so 63. Let me try again. 63, there we go. X power 6 minus 6 x power 5 plus 5. So that's the whole story to this derivative here. So the process on this one is if we differentiate a square root using the chain rule at the same time, this whole root just goes into the denominator with a factor of 2. The inner function we differentiate, and it just lands in the numerator in that kind of way. And even though this is a whole new derivative, the natural logarithm, there's no difference. It's pretty much the same process. It's just that the outer formula follows this rule for the differentiation this time. So we'll try that out, see how similar it looks to the one on the right. Any questions, folks, on finalizing that derivative there? Okay, so let's take a look on this one. It's a chain rule, once again, because it's not just natural log x. In place of that x, we have a degree 7 polynomial with 4 terms altogether. But the thing that went on the inside, just like on the problem on the right, is the inner function. So there's function 2, inner, once again. The outer function, slightly easier to highlight this time, is the natural logarithm function. So there's function 1, outer. Now we have to follow this format for doing the derivative. And we can say, starting this off, dy dx is going to be equal to, first, it's the derivative of the natural logarithm, which goes 1 divided by x. I'll put just a big placeholder there in the denominator for x to emphasize that's the x that we're throwing here. Then we multiply by the derivative of the outer function. And so far the process is basically identical, except it's just a different derivative. So there's no square root, there's no times 2, it's just x. We didn't even need those placeholders. Those are just there to visually see how the chain rule is tracking through. So in place of that spot, we're going to put in 9x power 7 minus x power 6 plus 5x minus 11. And then do it again over here. 9x power 7 minus x power 6 plus 5x minus 11. And at this stage, we're just about done. We're going to use the same strategy that we took here. When we differentiate this portion, it's multiplying a fraction, so it just goes up into the numerator. So on the next step, we get dy dx equals 9x power 7 minus x power 6 plus 5x minus 11. That fraction bar looks a little dramatic, didn't have to be that long, but let's go with it. This derivative is the same as before, 63. X power 6 minus 6 x power 5 plus 5. So even though we're in a new landscape, that's the whole analysis on the chain rule. And notice how close it looks to what we did before. If it was a square root function, that's a pretty close analogy. Only difference is there's 2 times a root, and the inner function went there. Here, the inner function just drops into the denominator. Well, we didn't use any properties of logarithms whatsoever on this one, but this is still a massive and major hint for a lot of the problems we'll do in these notes, and same with the ones you're going to see in the homework exercises. But any questions at all getting through that one? Okay, let's see what else we could get into. This one's another natural logarithm. They're not all going to be natural logs, so we'll have things like log base 7 coming up, so we can practice both formulas at the same time. The issue on this one is, if we're doing natural log of 5x e to the x, there's actually a lot going on there. It's absolutely the chain rule. If we didn't use properties of logarithms, we have an inner function, 5x e to the x. But when you differentiate that inner function, it's a product rule as well. So this is chain rule combined with product rule, and it could be a lot of work to get through all those steps. You can get the right answer by taking all those steps, but there is absolutely a better way to go on this. Oh, that's the wrong stream. Let me try again. Properties of logarithms absolutely have something to say when things are multiplied together. That's really three things being multiplied. If it's just two, you have log base b of x times y. You can say the logarithm of a product is the sum of the logarithms of the individual factors. So let's use that right here. And in fact, let's cite it on paper as well to emphasize each differentiation, or excuse me, each properties of logarithms that we use to help with the differentiation. So even though this is stated with just two factors, this extends to three factors, 3 million factors, just has to be a finite number of factors inside. So down below, this isn't the derivative at all, but we can say f of x can now be rewritten as natural log of the first factor, 5, plus natural log of the second factor, x, plus the natural log of the third factor, e to the x. And another hint is, don't stop when you just use one property of logarithms. Oftentimes there's more, and there absolutely is more we can use on this. Anyone happen to see anything here that could simplify even further? Yeah, absolutely. That natural log e to the x, it's still a complicated derivative. It's a chain rule as it stands. But just like Jude said, that simplifies too. That's property number one in the properties of logarithms. It's just kind of hard to track, right? Because these are written very, very generally with a generic base b. And we're looking at a specific base, natural log. Let's put that property on paper, but also, wrong one. Let me try again. We're going to put it on paper, but also rewrite it for the case where we're looking into a natural log. So there's the property of logarithm again. But for our context, it really would be expressed this way. So in place of b, we're going to write the base b equals e. Takes us to a natural logarithm. Here, this would be, instead of b, it's e now to power of x. And the result is just x. But actually, we were using and abusing that a lot in the last section notes. We were solving equations, and anytime we saw a natural logarithm right next to a base e, we said that's a cancellation, and it really is. So the idea here is use as many properties of logarithms as you possibly can. Don't stop at just one set, because now that it's written this way, f of x equals natural log 5 plus natural log x plus just x now. This is a really, really fast derivative at this stage. So all we did is algebra on 2 lines. Now we'll write f prime because we're differentiating. It is tricky, so watch out for these on exam 2. And we'll see what the derivative of this would be, right where the red dot is. What would that come out as? While we're thinking about that, I'm going to load up a calculator. Forgot to load a lot of things today. Okay, let's imagine we saw this as a real problem on exam 2. It might seem unfair because I was just mentioning you won't be differentiating any logarithmic functions on exam 2, but that one is fair game. And that's because it's not a function that varies with x. This right here is a bona fide constant. You'll have a scientific calculator available to you, so you could just put it in the calculator, observe. It's just that. It's really just a 1.61 if we round it. That's its exact form. The properties of derivatives say the derivative of a constant with respect to x is 0 because that is constant. So watch out for those. You could get weird things like e power 5, maybe square root 2 pi, even natural log 5 could come up, and you have to know there's no x whatsoever, and it's not multiplying anything, it's being added on. That goes to a 0. I'm going to write it in this time. Usually we would skip that, but I think it's a good one to write in just to emphasize that part went to 0. It's not 1 over 5 whatsoever. But this one is. The derivative of natural log x, because there's a true x there, becomes a 1 over x. And the derivative of just x itself becomes a 1. Because I took that extra step, we have to simplify further. The derivative of f at x is nothing but 1 over x plus 1. And that's kind of crazy when you think about this. You could, just as a kind of a challenge problem, don't use properties of logarithms. Differentiate this from scratch. You're using chain rule combined with product rule. It gets messy, it kind of blows up, but it will simplify all down right to that. So this is the value of properties of logarithms. It's making the calculus a lot more amenable, getting us through the steps pretty much in one step once we get the function in a nice form. Well, part B, in my opinion, is trickier than part A. Part A is just hit it with the chain rule, nothing fancy going on with properties of logarithms. But part B is tricky because now we're working 2 skills at once. Well, really 3 skills. Ordinary algebra, combined with properties of logarithms, combined with calculus all at the same time. So we'll definitely practice more of these in the notes. And essentially that's what's going on with part C next. It's messy. We have 15x times log base 7 of the cube root of 2x minus 8. So lots going on there. Again, that cube root might be hard to see, so we'll blow that up. Well, we can do a little bit with this. We can clean this up. Because if you see a root inside of a logarithm, just like we did on example 1, that's really a power of 1/3, and properties of logarithms can help out with this one. So following the strategy of look before you leap, let's not differentiate it yet. Let's simplify this function. We'll begin by saying h of x is 15x log base 7 of, I think a bracket looks a little bit better here, log base 7 of 2x minus 8 to the power 1/3. And now that power 1/3, we can use property 7 that we see here. Looks like P is for power is the idea with that property 7. So there's the property. And here's the relevant part highlighted. An exponent inside a logarithm becomes a coefficient and vice versa. So there's that exponent, and we can just jump it right in front of the fraction. So h of x on the next line becomes 15x times 1/3 comes out as a coefficient now, multiplying log base 7, and I'll drop the bracket and just write now 2x minus 8. So there's that property with 1/3 now coming out as a coefficient. And that means it reduces a little bit, that 3 divides into the 15, making it a 5x. And so now h of x is 5x times log base 7 of 2x minus 8. Well, it's been just pure algebra all the way to this step. We have to know that this is the stopping point for properties of logarithms, because a plus and the minus on the inside messes everything up algebraically. Again, we've solved this in a lot of things. For example, if you have the square root of 3x plus 5, it's absolutely not the same as the square root of 3x plus the square root of 5. They come out differently. And same issue with logarithms. log base 7 of 2x minus 8 is definitely not log base 7 of 2x minus log base 7 of 8. That 8 barely made it. So we're stuck with this one. That's okay. If we're going to do this derivative, the nice concept that this will review is it's now become a product rule. So we'll see exactly how that goes, working through the steps. So for the product rule analysis, there's really two functions. There's 5x. And if that x were just gone, and it's 5 times log base 7 of 2x minus 8, it's no product rule whatsoever. It's just the constant multiple rule. So it's the fact that there's an x multiplying that 5 that means we now have to use product rule at this stage. So let's work this out carefully. The derivative of h at x. First, any product rule always looks like this on paper. Don't forget your primes, and there's a plus for product. So if you like thinking in terms of laying down a structure, dropping in your functions, this entire structure right here conveys a product rule in one go. Then we take whatever the functions were, 5x goes into the first slots, log base 7 of 2x minus 8 goes into all remaining positions. Okay, so we're nearly through this. And that derivative right here isn't too bad. Derivative of 5x is just 5. Then we copy all the way to this line, but that derivative is a little bit more tricky than it looks. So let's take our time with that spot right there. First issue is it's not a natural logarithm any longer, so the formula is a little bit more built up. Let's put that formula on paper. Just as a reminder, the derivative with respect to x, or we could just say something prime like we wrote here, of log base b of x becomes 1 over x times the natural logarithm of b. So what that then tells us is, let's comma over. I'm going to write it in the same way. You could say d by dx, but I'll use a prime symbol just to give some parallelism in the notation. If you take log base 7 of just x and differentiate it, whether you put a prime or d by dx in front of it, it's this formula. You get 1 over x, just like the natural logarithm, but then you multiply it by the natural logarithm of the base, which is 7. So following the highlighting, that's how the derivative of this function will go. But again, there's more to this story because that's a chain rule problem as well. We just said what it looks like for x, but we have 2x minus 8 on the inside. But this gets us started. So let's look into just this one piece right here. We'll work out the derivative and then plug it back into the entire derivative, h prime at x. So now we're focusing on how should log base 7 of 2x minus 8 go as per the chain rule. We'll analyze it just like any other chain rule problem. I'm not using the same color coding because we already used up blue and green for the product rule, but it's the same idea. Whatever is right here inside another function, we call the inner function. So that's the 2x minus 8 on this one. So derivative 2, inner. Then the log base 7 function, much like the natural log function on example 2, that's going to be function 1, outer. And we just happen to know exactly how to do that derivative. It's right here on paper through the formula right here at the top of the notes. So when we do this derivative, here's what it's going to look like. Start with the derivative of the outer function first. It goes like this, 1 over a variable x, but we can't put x, we'll put it in a placeholder. And then we have to multiply by the natural log of 7, the base of that logarithm. Then we multiply by a new derivative, chaining it on. We're just going to throw it into the numerator overall on our next step. And once we have these two placeholders here and here, we swap in the inner function in both 2x minus 8, both here and here. So that's how it starts. It's just like any other logarithm. 2x minus 8 goes down into the denominator. It's to base 7, so we include natural log 7. Then we multiply by the derivative of 2x minus 8. You know that's just a 2, so 2 is going to multiply into the numerator, and that's the whole story of this one. We get 2 over 2x minus 8 times natural log 7. Nothing simplifies here. 2 and 2, or hang on, that's kind of a lie. It does simplify, doesn't it? You could factor a 2 out of that denominator. For some reason, it just didn't occur to me. Usually, we wouldn't cancel 2 to 2 here, unless it also cancels on the other factor. So that's the derivative. Let's simplify it, because we might as well now that I noticed that. On the next line, we could write that this is 2 over. Factor 2 out of that group, leaving behind x minus 4 times natural log 7. Then we get a bonus cancellation. Those 2's are gone, leaving a 1 in the numerator. So we have 1 over x minus 4 times natural log 7. And that means we're essentially done with this derivative. This entire piece right here, maybe box is a bad idea, it makes it seem like the answer. This entire piece right here is just going to plug into this spot. So we're about ready to finalize the derivative. H prime of x is now the derivative of 5x. That one's not so bad, we just get a 5. Then we copy in log base 7 of 2x minus 8. Still copying, plus 5x times this whole derivative right here, which we've worked out carefully as 1 over x minus 4, times the natural log of 7. So that's the whole derivative of that original function on the top. You know, it does simplify just a little bit. That 5x can go in the numerator. It cleans it up a little bit. If you left it on paper like that, again, I'm not going to be super picky on how you format this. There's no cancellation here, so you wouldn't lose points. That was meant to be enter. But if you were typing this into WebAssign, sometimes it is a good idea to make it slightly more compact. Another competing answer is 5 log base 7 times 2x minus 8 plus 5x over x minus 4 times natural log 7. So now we have the full view of that original function's derivative. This is absolutely the worst one on the notes, I think. This one takes a lot of work to get through. And that's just because it was combining multiple rules. Product rule together with another chain rule at the same time. Well, any questions at all, folks? Navigating this one? Okay, the next example we're going to take a look into is basically kind of a challenge problem where the whole point is properties of logarithms, really. So it comes in 2 parts. It says, expand the function fully using properties of logarithms. And that's a pre-calculus concept that you might recall from back in the day, but again, it is a review problem we're going to work out carefully. Once we have this fully expanded, we'll differentiate what we get in part A. But again, the major punchline to this whole problem is just practicing properties of logarithms one more time. Let's take the complete set. There's lots of properties going on in this one. Let's throw them all into the list. Not everyone is relevant, but it's good to have them just ready to go in case one of them comes out as being relevant. It's log base 5, so we have to be mindful of that when we take the derivative. And it looks way worse than the last example. But you know what? This problem is not as bad as the last example. We just get through the properties of logarithms, take whatever chain rule we have to take, and then the whole problem will be over. So let's work through this carefully. If you're really good at this, you can do it in one line if you've had a lot of practice doing this kind of thing. But if you wanted to divide this up into stages, I'd say this is a good start. Break up the quotient, the fact that something has been divided, and you get a minus. You know, while you're thinking about that, it's kind of satisfying to know that if you're doing, say, a product rule, f times g, you get f prime times g plus f times g prime. So the key issue with the product rule is you have a plus. And same for this product rule, property number 5, there's a plus in the middle. And if you do a quotient rule, f over g prime, you get f prime g minus f g prime divided by g squared. And there's a minus in that quotient rule. And same with property number 6 down below. The quotient rule for logarithms has us take the log base b of the numerator minus log base b of the denominator. That's kind of nice to see the parallelism for the signs, even though this is differentiation and logarithms, two very different concepts. It's nice to see the signs kind of match up with those concepts. So to start this off, I'll highlight the property we're using first. The quotient rule for logarithms says that this just is log base 5 of the entire numerator, x cubed, times the 5th root. You know, let's write that 5th root a little bit better while we're at it. 7x minus h to power 1 over 5. We're going to need to write it that way eventually. Then it's minus log base 5 of x power 5 plus 3 raised to power 4. So that's the quotient rule used. Now, next thing we could break up is that product right there. So we'll use the product rule for logarithms. And on this one, we can also use another rule, the power rule, rule number 7, make that power 4 come down as a coefficient. So on the next level, t of x, I don't know why the function's called t. T maybe for tedious. There's lots of steps to take before you even differentiate. But with that plus there, we get log base 5 of x cubed. Convert to addition for where you see that multiplication. I think I said that weird. For that multiplication you see there, we write down a plus through the product rule, then log base 5 of 7x minus 8 to the power 1 over 5 rather. And we can move that 4 down. Let's do it on maybe the next step. Minus log base 5 of x power 5 plus 3 raised to power 4. Let me fix that 5 there. So we're done with the product rule. And now we have an exponent here, here, and here. All of those exponents come down through this power rule right here, rule number 7. So when it says expand the function fully, this would be a bad step to stop at, because if we were to differentiate on this line, it's a chain rule right here. This one's a chain rule, but there's actually 3 functions. It's a longer chain. There is the innermost function 7x minus 8, the middle function power 1 5, and then the outer function log base 5. That's 3 functions in total. And same with this one. But run through the power rule 7. Sometimes that's an easy one to forget, and the function is even nicer. The function we really want to differentiate is t of x equals, this 3 comes down, 3 log base 5 of just x. Now it's a nice derivative. Here, 1/5 comes down, 1/5 log base 5 of 7x minus 8. You know, this one is still a chain rule, but just 2 functions, so it's much, much more manageable. And this power 4 comes down, multiplies the negative sign, so negative 4, log base 5 of x power 5 plus 3. Having trouble finding number 5 today. Let me fix the penmanship there. I would consider that fully expanded. Again, there's no rule that could break up a sum or a difference like we see here and here. So at this stage, we're ready to get started to work out the derivative. Well, all of that was pure algebra, no calculus whatsoever. But algebra and calculus, they don't exist in isolation. Sometimes to do the calculus efficiently, you have to involve a good amount of algebra, like we just did. So think of this again as maybe not the world's best exam 3 question or final exam question, but more it was just an opportunity for us to really practice these properties a little bit more. Any questions before we go to differentiate? Okay, last thing let's put down on paper is just a reminder. We have log base 5 of x and some compositions on the right. So we'll use this formula. Derivative with respect to x, let's just write it in with log base 5 this time, is 1 over 5. Let me try again. 1 over x rather, times natural log 5. So we'll use that formula 3 different times. Now we're finally differentiating. Let's call it t prime at x. This one is just a constant multiple rule. The constant 3 stays in position right where it is. But then the derivative of log base 5 of x puts x natural log 5 in the denominator. So we'll just throw it down here. And I don't know if you can hear this in Zoom, but my computer just got angry. It's working really hard. The fan's spinned up a bunch. Sorry if that's distracting. So the derivative of this takes the x, drops it into the denominator. Hope the computer doesn't blow up. It sounds like it's really angry all of a sudden. Then we multiply by natural log 5. So that's this whole formula. We just have a 3 in the numerator through the constant multiple rule. But then when we move over to these, they're chain rule problems. We have an inner function here, an outer function, also a constant multiple rule, then another inner function here, and another outer function. So it's organized like we did before. There's the inner and there's outer. And again, here's function 2, or derivative 2 will take inner, and derivative 1 will take outer. So if we can get through one, we can absolutely get through the second one. It'll be the same kind of thing. First, 1/5, because it's multiplying, stays where it is. I'm going to write out this way and just put in more fractions and then combine them to simplify in the next step. Next, we're taking the derivative of the outer function. So log base 5 goes like this. 1 over whatever your input is, put in a placeholder, multiply by natural log of 5. Then chain rule says, multiply by a derivative that goes like that. Next, throw in the inner function, 7x minus 8, in both of those positions. So we got through one, we still have to finalize that derivative. But now we just move on to the next. Go -4 times. We can do it once, then again, we can do it again. Same kind of process, just a different inner function this time. Go 1 over a placeholder times natural log 5, multiply by a derivative, throw the new inner function inside of both, x power 5 plus 3 here and here. So it's just 2 more derivatives to get through, a little bit of simplifying, and we're home free on this one. But even though this is starting to look pretty messy, it's a good idea to think in these terms. Imagine you differentiate that from scratch, no properties of logarithms whatsoever. That would be the outer function. This would be the inner function. But then you have to multiply by the derivative of that as an inner function. And we have never done a derivative that convoluted. It would be a quotient rule combined with a product rule, combined with a chain rule here and a chain rule here. So 2 chain rules altogether. the algebra would just go on and on and on. And eventually, when you simplified it enough, it would look like this. So we're getting the same exact results. Only difference is we're not going to add up our fractions. We're going to leave them expanded. Here, it would simplify to something that you could divide the denominator into and get this result after we take our final step. So here's our end statement on this one. Well, maybe a couple more, one more to simplify. Copy 3 over x natural log 5 plus 1 over 5 times. Let's leave the numerator blank and put in down below, copy 7x minus 8, natural log 5. And then this whole derivative right here is just a 7. It goes up in the numerator, and we're done with it. So now we move on to the next. Go minus 4 times, leave the numerator blank, copy the denominator, x power 5 plus 3, natural log 5. Now we do this derivative, we push it up into the numerator. Since we're multiplying a fraction, it ends up here. And that derivative is just 5x to the power 4. And if you leave it just like this in this format, I would give full credit to an expression like that. I think WebAssign would take it as full credit as well because nothing is canceling. There's no big simplification here. If you took one additional step, again, it's easier to type into WebAssign, so it's a good idea. Here's the last step I would take. 3 over x natural log 5 plus 7 over, I'll write this 5 natural log 5 over 7x minus 8. Just bring the constants up front. Really, it's up to you where you want to put them, so any order is just fine. On this one, I'm going to leave the negative in front, multiply 4 up into the numerator, so we have 20 x power 4, divide by x power 5 plus 3, natural log 5. So there it is. And one thing you never have to do on these is you absolutely don't have to add up, subtract the fractions. You can always leave it just like that. WebAssign expects you to type in just 3 different terms. Well, I don't think there's one quite as hard like this as WebAssign. Again, the major takeaway on this problem is really more about part A, practicing with logarithms. And then we differentiate it because, I mean, it's a calculus class. We might as well differentiate it too. But any last questions at all, folks? Getting through this kind of gnarly problem right here. Okay, again, it's kind of hard to appreciate just how much properties of logarithms really help. So if you're ever bored one day, if you're having trouble falling asleep, take this problem, differentiate it from scratch, no properties of logarithms, and see how much paper you'll use. It's a really good algebra and calculus challenge. Try to get to this. And if you can, I would say that shows a high degree of mastery of product rule, chain rule, quotient rule, all together in one in a really hard problem. But if you see these on WebAssign, treat yourself to the properties of logarithms. That's the major takeaway for how these problems are supposed to be done, really. Well, these are most of the concepts in this section. I have just one more additional random formula. And apologies on these notes. This is the one set of notes where I don't have an actual application on this one. There are really good applications, but I wanted to make these set of notes a little shorter because the next section we're going into, chapter 4, is all about applications. Then we'll use these properties for all the function derivatives, including logarithms, in that next chapter. So here's just a random formula that I wanted to end the lecture on. It's really weird when you take a look at it. The derivative of the natural logarithm of the absolute value of x is 1 over x. And it's weird because we absolutely do know that the derivative with respect to x of natural log x, it's absolutely true that that's just a 1 over x. And that's what makes this weird. If you throw in the absolute value, it says no change whatsoever. Absolute value of x could be stated in a couple ways. It's algebraically the square root of x squared. As a piecewise function, it's x if x is bigger than or equal to 0, and negative x if x is less than 0. And somehow, some way, when you differentiate that thing, you just get a 1 over x. It's pretty random and strange in a certain sense. The major reason we're discussing a random formula like this one is this becomes relevant with integration in chapter 5. So it's one of those formulas where it's hard to say what the role it plays is right now until it suddenly becomes super relevant and we're doing the opposite of differentiation, looking into the integration process. So there's the random problem right there. The derivative with respect to x of natural log x. We're going to calculate a derivative here, then evaluate it when x is 2. I felt like this one is so weird. It's probably a good idea to discuss why it's true as well. Because if you don't believe it, I understand. It doesn't look like it should be true. This looks like kind of a lie on paper. Let's discuss just really briefly how this one really works. I'll put a border here to say the formula is over. Let's imagine you're differentiating with respect to x, the natural logarithm of absolute value of x, but you had no formula. Here's what you could do. You could swap in what the absolute value of x is. It would mean you're differentiating with respect to x an entire piecewise function. It's natural log of just x when x is positive, but when x is negative, this part right here, the absolute value of x turns into a negative x. So it'd be the natural logarithm of negative x when x is negative. So if you differentiate that, it'll still be a piecewise function, but differentiating a piecewise function just says differentiate each row. You take the derivative on row 1, the derivative of that natural log x is just 1 over x, and this is only relevant when x is bigger than or equal to 0. Let me think about that a little bit harder. One small problem. This is irrelevant when x is bigger than or equal to 0. And checking out values, you can take a natural log 5. You cannot take a natural log negative 5. So if your input is negative, you have a problem. But if your x is negative, you throw in a negative sign, that's okay. It becomes positive. My problem is right there where the red dot is. You cannot take the natural log of 0. That's undefined. So I need to peel that part off. It's relevant for absolute value of x. It's not relevant to the natural log. You cannot plug a 0 inside there. So sorry for the distraction on that one. It has to just be strictly greater than 0 there. Now next, if you're differentiating natural log of negative x, it's a chain rule, but you could say it's this as well. Natural log of negative x prime, to say differentiate it, is also natural log of negative 1 times x prime. Then you just use the product rule right here. This becomes equal to the natural logarithm, or hang on, getting mixed up on that. No, I can't break that up in the way I thought. I was going to try to break this up with properties of logarithms, but no, you can't put a negative 1 inside there. That's undefined once again. So my approach right there isn't going to work. We just have to hit that with a chain rule. Sorry for the backtrack on that one. But we've got good practice on the chain rule. Here's how it will go. Natural log of negative x, now through the chain rule, and this is defined because negative x is positive when x is negative. We'll treat that as the inner function, natural log as the outer function, and here's what will happen. You'll get, for the derivative of the outer function, 1 over your input. So it's just another chain rule process like before. You multiply by the derivative of your input, and this time the input is negative x, going like that. So when we work out to that derivative down below, well, negative x stays right where it is. But the derivative of this negative x becomes -1. And here's where a mathematical miracle occurs. Signs cancel. And you get 1 over x again. It just inputs right back here. This works when x is less than 0. My idea of properties of exponents were irrelevant because you can't break up a -1 natural log. But the idea is, if you work really hard and break up absolute value of x like this, you're mindful of the domain. You don't allow x to be 0. That's impossible for a natural log. Differentiate both rows and you get 1 over x both times, when x is positive, when it's x negative. And then you just put it back into the overall formula. That proves this is a bona fide formula altogether. Let's put a box on it to emphasize that formula. The derivative of the natural log of absolute value of x is absolutely 1 over x. That's the takeaway. This is just the discussion that allows us to do one more chain rule and to show why it's plausible. Well, that discussion on the formula is longer than I thought it was. Sorry about that. But any questions about the formula itself? Okay, well, here's the last problem for the day. Again, we'll come back to this problem. It'll become a really major deal when we're in chapter 5. But for the moment, it's just an oddity. But it's going to allow us to differentiate this problem really fast. It's another chain rule, just like on example 2. That's the inner function right there. So it's derivative 2, inner. The outer function is the natural log x. So that's function 1, outer. And my highlighting kind of is hiding something. Let me try to do a little bit better target highlighting. The inner function includes the absolute value as well. But that's okay. If you differentiate an absolute value function, you're just going to get x down in the denominator. So absolute values vanish. We just multiply by the derivative of what's inside without absolute value now. So we can say dy dx is going to be equal to differentiate the logarithm. Whether there's absolute value or not, our formula above says it's irrelevant. It just does this. Your input goes into the denominator. You multiply by the derivative of whatever the input is, and just copy in that inner function now. X cubed plus 4x squared minus 1 here, and here. So the problem is nearly at its conclusion. We just need to finalize the derivative and then evaluate it. So dy dx is now copy the denominator, leave the numerator blank for the moment. X cubed plus 4x squared minus 1. That as a derivative becomes 3x squared plus 8x. The problem one is to do even more. We're going to evaluate the derivative when x is 2. But that was the major meat of the problem. Just get the derivative itself. So now for the evaluation, dy dx when x equals 2 gives us, I'm just going to put a placeholder everywhere x occurs. So it's 3 times x squared plus 8 times x. There was an x cubed here plus 4 times x squared minus 1. And whatever the input is, we drop into all of those positions, here, 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 and here. Now it's turned into an arithmetic problem. So we have 4 by 3 for a 12 plus 16. Then it's going to be 8 plus, this is 4 times 4 for 16, minus 1. So numerator is now 28. Denominator is 24 minus 1. For a nice prime number, 23 means the fraction doesn't reduce. And that's the conclusion on this one. Really, the whole purpose of example 3 was just to use that formula right here by the red dot. So we worked out another derivative. The idea is absolute value bars or not. It's just like example 2, part A. And then we plugged a number in to finish off the problem. Well, any questions at all, folks, getting through the rest of these notes here? Okay, well, we did it, folks. This is the last of the content for derivatives. Everything we go forward is now just going to be using properties of these derivatives. And then in chapter 6, we turn to that word I said before, the integration problem, where it's not going to be about slopes of tangent lines. It's going to be the area under a graph between the x-axis and the graph itself. So in some weird, mysterious way, there's a great analogy that says differentiation, finding the slope of a line, and integration, finding the area between a horizontal axis and a curve. They're actually the opposite problem, which is mind-boggling, but we'll get there in chapter 5. But have a great night, folks. If you have any questions at all while you're reviewing for the exam, don't hesitate to reach out either by email, hitting the Ask My Instructor button, anything like that. If you're behind on any quizzes, try to get them in as soon as possible, and I'll be working on grading them as fast as I can so you can get your feedback on them. But have a great weekend, folks. We'll all meet officially once again on Thursday's class. For the in-person section, we'll meet on Tuesday the 10th. Have a great night, folks. Take care.